Meanwhile, colleagues online, if you have any questions, you have time to discuss. I saw some options. I saw some options 11, 7, and 12 in chat. Great. All right. Yeah. So delivery process orchestrator, for example, that's one of the trickiest components, and of course, we need to double check if there is no other way to ensure our security objectives yeah, do not require verification of this component 7. Navigation 12 and emergency landing, yeah, these are crucial, especially for the second security objective. However, if we add security objective number 3, then obviously we would need to verify, to put into TCP, Trusted Computing Base component 13, for example. We make security assumptions. Yes, we do. Here we have at the moment just one security assumption, that is a trustworthiness of sender IT system, the system which originates basically delivery machines. But we only assume trustworthiness at the, let's say, departure point from this system. We do not assume trustworthiness of data transmission environment. That's why incoming data flow is low in integrity data. Low integrity data, there was a question that is actually data that potentially contains modified. Just to finish, high-low integrity data. So high integrity data coming from trusted components. So this is the data which we can basically trust that and does not contain any modified malicious parts. It will not contain any SQL injections and so on. Whereas low integrity data comes out of untrusted components that potentially can contain additions which spread some attacks. So that's low integrity data and any trusted components. So first of all, we have yellow components that will have to clear this data and remove any potential harmful additions, either block the data or proceed with data. Proceed with the data after this clearance that only useful or corrected part is sent further. And another question, how can we ensure and enforce security assumptions? These are security objectives for those systems. So there obviously is another team which is responsible, for example, for sender's IT system. And this team will have a security objective to ensure trustworthiness of this data out, of this system data output. Might be not every component of sender IT system is trustworthy, but at least the critical ones. This is basically the same exercise that we do right now with this delivery drone. It will have to be repeatable or done in a similar way with this sender IT system. This is the way how we ensure security assumptions. Okay, let's proceed. And okay, I hope colleagues online, you still see the screen, which is security objectives and assumptions for our drone. Yeah, just let me know. Send me plus any other sign that you can steal it. See, okay, thank you for the hand raised. Good, colleagues. The question is: do you want to continue these exercises? Let me know. If it's more or less clear, we will skip to the next section. So, looks like we will skip. So, what will happen after this slide? Okay, next exercise very similarly, but needs the false security objective that safe distance from stationary objects. And you see appeared the component number 13, LIDAR. Yeah, and obviously, since this source is essential for number 4, then we probably will have to make it trusted, yeah, move it into trusted code base. And finally, kind of result, yeah, or solution on these 4 security objectives and our delivery drone. You see on this screen that we also added your two thinking too far away, probably don't see that we added in the circles qualitative estimations of components like double S the small symbol for LIDAR, or we also have introduced component number 17, information processor from LIDAR, that we also send this information into not just one component number 8, but also to component number 7. Yeah, so we spread this information to several components with the idea to exclude from trusted code-based component number 8 because it's complex and large, and we don't want to keep it in our TCP because of the cost. Nevertheless, you see that overall we have quite many components in our trusted code base. So, we still have complex and large components among those yellow and green ones. That's actually not good because it means that design of the system will be very expensive. And there are at least 2 options how to proceed from this point. So, what do you think? What are possible options how to make the system cheaper? Any ideas? Maybe also from online. You see, everything what is not red is actually expensive. Yeah, everything which is more complex than simple and larger than small is very expensive. Okay, so and we want to be in budget with our delivery drone. Basically, we come up with such an architecture and say that actually for every trusted component, we need to do full fuzzing. Yeah, you know, fuzzing, police. Yeah. So, component verification will cost, say, $1 million, $5 million. Yeah, it's too much. So, what can we do for this thing? The redesign, okay. And what shall we do in this? What should be the goal of this redesign? Right. Minimize. Right. So one of the ideas that it takes so much that we redesign this whole architecture by extracting the most critical parts from these especially complex and large components to smaller ones. Yeah. And yesterday on the slides, you probably saw that we tried to minimize number of trusted components. The thing is that we minimize the number only if those components are small and simple. It does not make any sense to minimize the number because of size and complexity. It is much better to have 3 small and simple trusted components than 1 large trusted component, because verification costs of complex components, they grow, the cost grows exponentially, not roughly. Okay, so it's better to decompose further and ideally keep our trusted components small, simple, and in addition, further, we also minimize number of interfaces, especially those incoming errors. Those are most critical ones, because every incoming error that is attached our attack surface. If, for example, we have compromised movement control, it sends potentially incorrect data, maybe some data being try to exploit the vulnerabilities in our 7. It sends to 7. And for example, this camera, for example, this deleted process orchestrator, it has 1, 2, 3 incoming errors, and the more it has, the more difficult protection implementation will be, and the more expensive verification process will look like. Okay, so that is also quality criteria for our systems design. And with students, when we do these exercises, we also discuss how to redesign in order not just to minimize this code base, but also reduce number of interfaces of those trusted components. And that is a diagram you already saw yesterday from Kaspersky Industrial Security Gateway. That's kind of architecture, and it can contain dozens of components, potentially hundreds of components. And we only need to focus on very small part, the critical part of this system. So you understand from this picture, I hope even better, how important it is to concentrate the security relevant code in some isolated restricted area and make it small. Okay. So another question is, do you want to practice a bit on your laptops with the example? Some do, some not really. Those who want, we have two possible example assignments for you. First question, have you managed to open this diagram via link I sent you with the robot? Okay, so we will work with negative scenarios, and there is a link I will send in the chat. I will open it myself here. I will show it to you. Okay. I will send in WhatsApp chat this short link, and we'll discuss it now. So, in this document with architecture, there is a page called negative scenarios. And I just mentioned that as part of threat modeling, there was a question, what if we miss something? What if we forget some scenarios and so on and so forth? So right now, there are no formal methods that will guarantee completeness. We do expert analysis and modeling, including negative scenarios. And here we do analysis of every component. And as I mentioned, we visualize it using sequence diagrams. It doesn't mean that you cannot describe everything in plain text. You can, just it's more difficult to read and understand. In graphical representation, it's easier. So let me open them. Right. So when you open the link from WhatsApp chat, did you manage to open the link? All right. So you will see this diagram. This is the sequence diagram, and it contains scenario of attack through compromised connection or communication module. So what we showed here, we first of all, using red color, show that the component number 1 is compromised, and then we show how this attack basically could evolve. Yeah. Second, we see that there is compromised prescription coming to the central control system, and then we simply show that the whole manufacturing process, yeah, or this medicine producing process basically got went wrong, yeah. And our security objective, for example, related to technological process, got violated, right? So we visualize that because of this compromised one, and then compromised data coming on the second step, and this whole thing visualizes producing scenario that you already saw during high-level description of the system. So it goes wrong, yeah. And we finally, you see, we just write it here: violation of security objective number 1. We can describe this diagram as text. What you already know Plant UML tool? Anyone? Right. So Plant UML tool is very useful for especially for sequence diagrams. And you see that there's a text here. It starts with the title. And if I change text here, for example, 1, 2, 3, then the tool automatically updates the diagram text here. But it's not, the biggest, nicest feature of this tool. More interesting is how it renders the diagram itself. So all the connections here are described with plain text. And for example, we have here pharmacy to connectivity, data with comment request for prescription product. And here it is shown as step number 1. Also, it auto numbers all the arrows. Here we have request for prescription product. And we can easily modify this diagram through text. For example, I can make bidirectional this arrow, and then it will, change here in the tool. So I don't draw it myself. It's quite boring, yeah. Especially if you want to change behavior of the system. I do this through this text diagram code, and I receive a diagram is output. What else I can do? I can change color of any participant, any box here, any arrow. Yeah, I simply do it by adding red. For participant, you see it's on the right side. I just add, for example, now I want to I want to illustrate scenario that the central control system is modified. So I annotate this red. So this component number 3, you see it has become red here. And then I change the color of arrows. This is not red anymore because it's not compromised. But what will happen? Let's just think and then reflect it on the diagram. What will happen? I will also remove red color from the group here for the time being. Okay. What do you think will happen if central control system in the initial architecture is compromised? What is the worst case scenario? Let me know. Tell me. Any ideas? For this, okay, you have a look on the this process, how it produces the drug, and you also look at security objectives. So we have security objectives mentioned. It depends also on what we model in our system. Okay. Example here. We have only static production tasks are performed. So if central control system is compromised, what do you think? Can it lead to violation of this first security objective? If a central control system is compromised, if central control system is compromised, then what can anything wrong happen to the first security objective? You're right. Let me see what we have in chat. Wrong medicine. Yeah, right. In chats, well, basically, central control system can completely ignore whatever prescription arrived through communication. Just doesn't care. Yeah, it does. It will do what hackers wants our robot to do through the existing implementation, or if we have existing architecture of the robot. Then obviously, number one, security objective can be compromised. Then the second one, only authorized substances are used for production. Will it be compromised? Yeah, right. Also,
sure. It's just, it's all moments. Nothing. Always epic.
yes, also true. And if, for example, we don't have any safety mechanisms in place, like some walls around the robot, and there's our operator, our specialist, the man, nearby the robot, then theoretically with the arm, robot can harm this human, right? Human being.
It's like love. Basic way. Said, and damage one joint. I've seen it. Actually, it's equipment. Expensive.
Yeah, right. So it can be a problem to the robot. However, let's have a look at the model and what our business thinks about that. You see, the robot here as an asset was and harm to this asset was considered as average. It means that our robots might be expensive, but not as expensive as secure development of this robot to make it unable to harm itself. Right? Again, It's not about theoretical scenarios and make everything as secure as possible. That is what business considers as unacceptable, and what business is ready to pay for. So, as we see from this analysis, business is okay with actually losing robot hardware. It's not super critical. So, business doesn't invest money in if this particular situation, just this particular situation happens. But as you already said, actually the second security objective will also be violated, along with the first one, means that we can use unauthorized drugs or substances and basically ignore everything what is written in prescription. So this is critical. Okay. And we, in our sequence diagram, just visualize it. And then we, as a result, write that objectives number 1 and 2 are violated. Okay, let me see where it is. Okay, so how we do it? We basically make that step number 8. And for example, we can also we can ignore any instructions related to temperature setting. Also, we will ignore or potentially can ignore sterilization step. Yeah. And finally, we mark that these variables. The worst case scenario what can happen, and the results that violated objectives number 1 and number 2 if we just have these 2 objectives. Okay, so just try it and let me know if you have managed to modify this diagram. Why we ask also students to work with diagrams? Because this is how they also work on their own projects. These are course projects, for example, when they design some new system. It could be something that comes from a teacher, yeah, or from us, or they come up with ideas of their own systems. For example, I have students who actually works on control algorithms for manipulators, robot manipulators. And the whole story about this robot pharmacist grew up from this project of student. He was thinking just about control algorithms. I proposed to, widen the horizons and think of solutions and from security perspective. Similarly, if you have students who work on some systems without thinking about security, we can propose them to add to this chapter to their thesis, yeah, and develop cyber immune architecture, which includes the components that they actually are specialized in. Okay, so that is the idea how we can have synergy between courses also, like math, control, software development, anything, just we add this additional dimension. And the end is the whole, let's say, machine, yeah, the process, how we create new cyber immune systems architectures. And we ask them to think through functionality with our help, but then model their systems, also model scenarios, use cases. Negative scenarios mean scenarios when security objectives are violated. And through that, think architecture policy. Yeah, architecture policy, that's the diagram. with those green, yellow, and red boxes and connections within it. Have you managed to update the diagram? Or you want to? Okay. Okay, so what happens? What happens next? Ideally, every component is analyzed in a similar way. Yeah. Then once you have such diagrams, you fill in this table. Just a sec. You fill in this table on this page, negative scenarios. Yeah. And this short summary. Final result, what will happen. And then you basically, when you define architecture policy of the system, this is what you start with. We start with everything we have, everything untrusted. And we recolor in green or yellow only those parts which we from our modeling understand are critical. So just we saw from this first two scenarios that obviously communication and central systems are critical, right? So they do not influence on external on data transmission environment. Therefore, incoming error will always be red. Yes, that's why we will have to use some encryption mechanisms because in our network there could be already some malware, and that's why communication we shall draw in which color. Basically, the options green or yellow. Which color would you choose? Or communication number one. You need to choose on the level of integrity for component number one. From analysis, you saw that it has to be in TCP. So it will either be green or it will be yellow. Green can only receive green incoming arrows. If you have red incoming yellow arrow, it can only be yellow. So communication, which color? That's not important. We are talking right now about just this. This component. So green. Let's see other ideas. Okay. So it's I see. I almost lost you. I'm afraid. Yeah. A bit too sophisticated. So again, one is trusted. Can only be green or yellow. Green if everything which comes into this component is high integrity data. But I just told you that communication receives data from outside. It cannot be trusted by default. Then communication can only be yellow. Yeah. So communication will be yellow, and we will need to change color of this component. If that's homework, then this is what we would do. Next, we just model the central control system is also critical because we just saw from our modeling exercise that if it is compromised, it won't request for serialization step. It can choose for choose any other drugs and so on. Yeah. So three, so that's to be trusted. Now the question is which color? And now it is a bit more tricky. Yeah, because we have incoming errors from self-diagnosis, from measurement, from measurement of substance parameters, that from communication. From communication, incoming error will be green because it is trusted. Yeah, and out of trusted, we always have high integrity data. So in this direction, it will be green. Since it is trusted in backward direction, will also be green. This arrow, therefore, we can have bidirectional and green. What about the 3? So if we do some more analysis, for example, self-diagnosis, most likely there is no direct scenario when it is violating security objective once if compromised, right? So, and let's assume that self-diagnosis we can keep untrusted, red. Outcoming data will be red. Coming inside of our trusted component, central control system, then what color? Yellow. Yellow, right? Absolutely, right. Then this will be yellow. In the same way, we do the analysis of this entire architecture, coloring it according to our analysis, and following the rules, the notation rules. Yeah, that if we have incoming low integrity data put into our trusted component, it must be yellow. If everything coming high integrity, the trusted component is green. And then what we do, you see these circles here are blank. In these circles, the idea is that we put our own feelings for size and complexity of these components. There is no implementation yet. We cannot count the lines of code. It's from our experience. Maybe we will ask other experts who already did similar local robots. We might try to get evaluation, estimation of size and complexity. So, what do you think 3 will be? Size and complexity. X large, and that's size and complexity. Simple, medium, and complex. CXL, yeah. So, and that is relative estimate. Estimate, yeah. Again, we do not have absolutely precise grades, saying like 5 lines is small, yeah. 1,000 lines, medium lines, large, or it's large. It's that like, for agile development, planning poker. Who heard of planning poker? Have you heard? Heard? Okay. So it's a team exercise when a team tries to estimate complexity for particular development tasks. They haven't implemented anything yet, but they have experience maybe from similar tasks implementation. And then they all have cards with some numbers which reflect complexity, how they think of this complexity. Then each teammate just put a card, they kind of vote, and then they discuss about results. For example, one set complexity, Fibonacci numbers. Yeah, one set complexity is 3. The points, another one set it's 11. Other set 5. Then what happens? Those extremes, those who voted or said extremes, they asked why 3, why 11, and then they come up with some rationally, yeah, some explanations, and then team re-votes again. So it's all relative estimation based on experience. And in the same way here, we can say what is the simplest component here from our point of view. Just for example, server drives. Yeah, very simple hardware, a few lines of code which manages a particular drive. So let's assume this will be in our classification small and simple. Yeah, component. If this one is small and simple, how shall we rate that communication component? Again, watch. Okay, watch. For example, watch. The idea is, again, for us, it's qualitative analysis that we said it's an exercise for system design. After we finish this coloring step, and after we fill in these circles our own estimates of size and complexity, we will manage to judge how big is the portion of trusted code base in our system on qualitative level without implementing the system first. Yeah, we don't write any code, but right now at this point we can already see some space for improvement. Yeah, improvement potential. For example, we see right now that our central control system is great from functional point of view, but from security point of view, it's too expensive. So we might need to think which parts of this central control system we will extract from it, like we did in drone, yeah, and put into a separate component. What functionality will be of this separate security specialized component that we will be able to move this central control system out of TCP. And the question is, will benefit cover efforts spent into introduction of this approach? Yeah, so it's basically what you need to decide for yourself. In simplest way, it's just let's say personal opinion of an architect, how he or she feels about the components, and then it is support for this architect to start redesigning the system, and also kind of measurements and stop criteria. If we see that right now, from our feeling, all the critical components are small and simple, or at most medium and simple in terms of complexity, then we did a good job, and we can already start prototyping. Yeah, so this is what we do on architecture side. And since I already got design around out of time, let's back to the slides and go to some summary. So, first of all, it's not a brand new methodology. What you heard about the cyber immune development approach and cyber immunity in general, that's best practices summary, secure by design. This is what Alexander mentioned yesterday. All the use for decades in avionics and other industries. Yeah, we add more clarity on assets. What should be done on which phase? What should be done by business? How architect could better do his job. Then we give examples of artifacts and actually rather clear instructions how to work with these artifacts and how to learn how to work with these artifacts and each others. Yeah. So we also propose some gamification ideas that you can use to teach your students. And what you saw about this firefighter drone, basically it's just one scenario. Obviously, we can think of more scenarios with different systems, but showing the same basic idea that we need to minimize TCP by separating security critical code and minimizing those parts which are responsible for this security from other functional specific code. And this will help the students to get the idea and inspire for own projects. And those own projects, we say that, of course, if they use the Kaspersky operating system, that will be almost product ready, in the best case, but it doesn't have to use Kaspersky operating system. It can be used with any technological stack, any operating system. Just we need to understand overall TCP, what will be there. And if we go to some POCs, or especially for product, we need to understand that this operating system implementation automatically adds the isolation core, adds to, or adds up to the TCP. Yeah, because everything above is built on top this functionality. So I hope also agree with us, so that demand for security is growing. Yeah, and over the past years, growth is tremendous. A number of attacks, complexity of attacks, also attack surface increased a lot because of connectivity. Everything is connected, and it's very easy now to get attacking tools and scripts and try to attack some systems. Right. So we suggest that you start teaching your students cyber development approach, and we are ready to support you. So we have in Russia, we only have community. We have a Telegram channel, Learning Cyber Immunity. There are almost 400 subscribers to that channel, where we announce new courses and events like hackathons, for example. I just created this Telegram channel. Not sure if you want to join and have information about online courses in English. Let's try to use this channel. We can also use this WhatsApp channel for some time. Maybe it's for closer communication. Otherwise, feel free to email me or our colleagues. We will be happy to continue our cooperation. Thank you. Thanks so much. That's it from my side.